My name is Doyhenard. I'm a security researcher at the Onapsis Research Labs. And Onapsis is a company focused on enterprise software security. And among the different enterprise software developers, SAP is probably the most popular one, with over 400,000 customers, and there is 400,000 installations, and including 90% of Fortune 500s. And SAP develops enterprise software that is used by different companies to manage their business processes and their most critical assets. That includes their operations, their financials, their human capital, their customer relationships, supply chains, many others. And to do so, they provide different modules that can be included in the SAP system. And they are all based, or most of them are all based on web services that are accessible through HTTP. And this is true for both Java, ABAP, and even S/4HANA, which is their flagship product. And to expose these services, they use a proprietary HTTP server called Internet Communication Manager. Now, the Internet Communication Manager, or ICM, is used to handle all the communication that is between the SAP system and the outside world, like clients, for example, customers or employees, but also with other SAP systems and with other systems that can consume these services. And to communicate with other clients, there are different protocols that the ICM can handle, like P4, which is a proprietary protocol like RMI from Java, IIOP, SMTP, and the most important one and the main purpose of the ICM is to handle HTTP and HTTPS. And what's really interesting about the ICM is that it's present in all SAP systems by default. So all SAP installations will have this component, and it will be exposed by default. So this is part of what is called SAP kernel. And so any system like Java, ABAP, a web dispatcher, which is a load balancer, S/4HANA, the cloud, all are going to use this exact same proprietary HTTP server. Now, of course, we don't have the source code of this HTTP server, so we had to reverse engineer. I had to understand how this system worked, and this is probably the most important part of our research, to understand how it works, because then vulnerabilities are going to come by themselves. And so SAP does not provide a lot of information. They provide this small diagram that we can see in the slide, but we are going to abstract this to understand how this actually works. So to abstract this, and I'm going to abstract a lot of the internals of the architecture so that I can explain this in 40 minutes, I'm going to see the ICM as just a system that will receive clients' requests and responses. And first, when a client starts a TCP connection, the ICM will start a worker thread, which is just a simple thread, that will be assigned to this TCP connection to handle all the requests and responses. To do so, it will use an HTTP parser and also some internal handlers to actually try to resolve the request and generate a response. And if it's not possible to do it inside the ICM, then a different process, which is a Java or an ABAP process, will be used, because in there is the business logic of the SAP system. So when a request arrives from the client, the worker thread will try to parse it, will try to resolve it, and if it's not possible, which is in most cases that it will happen that way, it will send the request to the Java or ABAP process through what is called a memory pipe. I'm going to explain what is a memory pipe in a minute. Then the worker process will resolve the request, generate a response, send it back to the ICM, and the ICM will send it to the client. So what are memory pipes? Well, MPI, which is how they call memory pipes, is a framework that is used to support the exchange of data between the ICM and the Java or ABAP process, which I'm going to call worker process. And to do so, and to do it efficiently, it uses the shared memory to send MPI pointers that are just pointers to the shared memory. Even though it's called memory pipes, it's using shared memory. And when these memory pipes are sent, or when these MPI pointers are sent between the worker thread and the worker process, they are going to be sending a reference to an MPI buffer, which is just a buffer inside the shared memory that is a fixed size buffer of 65 kilobytes. And they will be reserved and free both by the worker thread and by the worker process using an MPI handler. So let's see an example of how this works. First, a request will arrive to the input-output handler of the worker thread, which is just a TCP socket with an internal buffer for every data that arrives from the TCP connection. And when the ICM is, or the worker thread in the ICM is ready to handle the request, it will read from this input output handler. It will reserve an MPI buffer in the shared memory using the MPI handler, and it will store the request there. Now, it will try to resolve it. It will parse this request. It will try to resolve it using the internal handlers, which I'm going to explain also later. And if it's not possible to resolve the request inside the ICM, it will forward the request to the worker process. And this will be done by sending the MPI pointer. Now, the Java RAVAP process will have a reference to this position of the shared memory, and it will generate a response for this request, which again will be placed in the shared memory by reserving an MPI buffer. And the reference will be sent to the worker thread. The worker thread will be able now to send this response back to the input output handler, which will forward it to the client. Finally, the MPI buffers will be freed, and the references will be lost. But I also said that the ICM will try to resolve the request using internal handlers. So what are they? Well, when the request is parsed, the parser will actually choose which handlers should be included in a list of handlers that should try to be used to resolve the request. And this is going to be done by looking at the URL. So depending on this URL, some of these handlers will be included and some don't. And what's important is that when a handler is able to resolve a request, it will just send a response back to the client, and all the other handlers will be deleted from this list, and the request response cycle will be completed. So first we have the cache handler. It's the first handler that will be used, and it's always going to be included in the list. And the cache handler will just do what is expected. It will look in the cache for a store object for the URL that was requested, and if it fails, it will continue. If it's able to generate a response out of that, it will send it to the client. Then we have the admin handler and the authentication handler. They are both present by default, but they are only going to be included in the list depending on the pattern in the URL. So for the admin handler is if the URL starts with the prefix /SAP/admin, and for the authentication handler, there are some hard-coded values in the ICM that will be compared to, and depending on that, it will be included or not. Next, we have the modification, the file access, and the redirect handler, which are not really interesting because they are not present by default. They need to be set before the SAP system starts in a specific configuration file. And finally, we have the Java and ABAP handler, which are just handlers that will be used to forward the MPI pointers to the specific process. As you can see, there is a specific function for each of the handlers. There are also some handlers, there are functions inside the ICM, and there are also some other handlers like the log handler, which is not quite interesting because it cannot generate a response, so we are not going to see that. So let's see an example of how the ICM will resolve a request using internal handlers. First, the request will arrive, and in this case, it's a GET request to /SAP/admin. So when the ICM is ready to handle this request, it will reserve an MPI buffer, store the request there, and then it will use the parser to select the handlers that should be included. Of course, the cache handler will be included. In this case, the admin handler because of the URL prefix. And finally, the Java or ABAP handler, which is also always included at the end. Now, it will call the cache handler, and in this case, let's say it fails. So now the admin handler will be called, and again, in this case, let's say it's able to resolve the request. So it will generate a response. It will not place it in the shared memory because it's not necessary to do it. And the other handlers will be deleted, and the response will be forwarded to the client. Finally, again, the MPI buffer will be freed, and the request response cycle will be completed. But what happens when we have a request that is longer than those 65 kilobytes? So it's bigger than the MPI size, the MPI buffer size, sorry. So again, we are going to have some problems because we are going to need more than one buffer for this. And I'm going to call this kind of request a long request, even though it's not that long. It's just like 65 kilobytes. But what is going to happen is that when this request arrives, for example, a request containing 66,000 bytes in the body, the worker thread will reserve an MPI buffer, and it will store the first 65 kilobytes. And this is because the internal handlers only need the headers of a request to resolve or to generate a response. So the ICM expects that if an internal handler is able to resolve the request, then there is no body. And in SAP, the headers cannot be longer than 65 kilobytes. Therefore, it's not necessary to store more than one, or to reserve more than one MPI buffer. Now, the handlers will be called, and in this case, only the cache and the Java or ABAP handler. The cache handler in this case will fail. And so now, when the worker process handler is called, the rest of the request is going to be placed in the shared memory, because the business logic, or the actual Java or ABAP process, will need the body of the request. So the ICM will reserve a new MPI buffer, or as many as is needed. It will place the request there, the rest of the request, and it will send both references to the Java or ABAP process. Now the Java or ABAP process will be able to generate a response again. It will store the response in an MPI buffer. It will send a reference back to the worker thread. And the worker thread will now be able to forward the response back to the input-output handler, which will forward it to the client. And now, as there were more than one buffer used for this request, instead of erasing or freeing each of these buffers one by one, the MPI free all buffer function is going to be called so that all buffers are freed. And that is all buffers associated with the worker thread. And now the references will be lost again. So let's see at the first vulnerability. So, as I said, the ICM is not expecting that an internal handler is able to resolve a request with a body. But what if we send a long request that is resolved by an internal handler? Again, we see a request which is a get to /SAP/admin and with a body of 66 kilobytes. And so what it will happen is that the worker thread will again reserve a buffer, place the first 65 kilobytes in this buffer, and it will call all the handlers. The cache handler will fail, but now the admin handler will resolve the request. And that is something that the ICM was not expecting to happen. So the response will be created, it will be forwarded to the client, and the handler will be deleted, and of course the MPI buffer will be freed, and the request response cycle will be completed. But we have more data from the previous request in the input-output handler. So what will happen is that the worker thread will read more because it's waiting for a new request, and it will place this request, or the rest of the request, the body, in this MPI buffer, and it will consider it as a new request. So if you know something about HTTP synchronization, then you will know that this is a big vulnerability, because we are going to be able to desynchronize any ICM, or the communication between a proxy and an ICM in any case. And that is because this request that we can see in the slide has nothing strange. It's completely RFC compliant. And so any proxy that sees this request will think that this is an isolated HTTP message, because it's a GET request to a normal URL, and it contains a body of 65, in this case of 65,417 bytes, which includes the entire body, and that is also the GET smuggle request. And when this reaches the ICM will actually split this, and it will consider that the last part of the body is a new request. So this will allow us to split the request and actually cause a desynchronization. Now you might think that this is not such a critical vulnerability, but remember, we found a vulnerability that is without authentication, and that is in a component that is completely exposed to the internet in all SAP by default. And you are going to see how we can use this and why the synchronization is so critical, because I'm going to explain how we can use this to either steal users' credentials, either steal session cookies, and also modify the behavior of the application. I'm going to show actually one example. There are others I'm not able to show in this presentation. You can read it in the white paper. But what I'm going to show is how to hijack a session from a user. And to do so, I'm going to use the NWA endpoint, which is also present by default in all SAPs, and it's an endpoint that is used to redirect users to the login URL. And this provides two interesting features. The first one is an open redirect that will allow us to inject something in the redirect, or in the redirect URL, actually in the host. So we will be able to change anything we want by placing something in the host header of the request. Of course, this is not actually a vulnerability. This is a feature, because in some normal cases, we are not going to be able to modify this in a victim. And also, the other important feature is that we will be able to reflect parameters. We will be able to reflect anything we place in the body of the request, in a post request and the query string of a GET request, in the query string of the redirect URL. Okay, as you can see, the line breaks will be replaced with spaces. So let's combine these NWA features and the synchronization to hijack a victim's request and a victim session. To do so, the attacker will send a payload, which is just a payload to an internal handler, or a request to an internal handler, that it will contain a smuggle request. When this reaches the ICM, it will be split, as we already saw, and the first part will be resolved by the internal handler, and the response will be sent back to the attacker. But the rest will be stored in the ICM, because in this case, the content length states that there should be 100 bytes in the body, but we can choose any amount of bytes we want. But as you can see, there is no body, so it will wait for more data. Also, you can see this is a post request to NWA, and with the host header being evil.com, which is a host controlled by the attacker. So when a victim issues a request to the proxy will forward this request, and it will concatenate it with the previous smuggle request. And it will use the first 100 bytes of this request as part of the body. So the response that will be generated by the ICM will be a redirect to evil.com, and this redirect will also contain in the query string the first 100 bytes, or as many as we want, of the original request of the victim. And this also includes the cookies. So when the browser of the victim receives this request, it will send a new request, when the victim's browser receives this response, it will send a new request, but in this case to evil.com, which is a host controlled by the attacker. So this request will not only contain what was expected from the redirect, but also the query string will contain the original request of the victim, including the cookies. So that way we will be able to hijack any victim's session and the cookies, and we will be able to actually take control of an application if we hijack, for example, an admin user. But for each request that we are able to hijack, we will need to send a new attack. And we don't want to do it, or we want to just send one attack and to make this persistent. And what's interesting about the vulnerability and why it's so critical is that we are not using any HTTP headers to attack this. So we actually don't need to inject any special or strange header to cause the desynchronization. So what is going to happen is we are going to be able to exploit this by using HTML forms or JavaScript. As you can see in the slide, I can create a form that is going to send a request to an SAP system with the URL being starting with /SAP/admin, so it will be handled by an internal handler. It will contain a padding that will make this long request. And at the end, will contain the smuggle message. Of course, the smuggle message is the post request to NWA, as we already saw. So when a victim receives this, what is going to happen is that the JavaScript that is found at the end will submit this form, and the attack will be created, but in this case, from the victim's browser. And we can also use this kind of attacks to in other vulnerabilities, like the one found last year in HI proxy, which again did not require any strange or invalid HTTP header, or in any case a forbidden header like a host or a content length header. So we will be able to use the same technique, but in this case using DNS rebinding to allow the browser and the JavaScript to send the extra headers. I'm going to show now an example of this. So in this tab, we are going to see the victim. And the victim is going to send a normal request to start page. And we can see that the response is 200. And in this request is also included the cookies of the victim. And nothing strange is going on until here. Okay, you can see the cookies. But in this tab, we are going to see the attacker, which is going to send the payload we already saw. This is a get to /SAP/admin. I'm going to use /SAP/admin because it's always present and it's easy. And at the end, it's going to contain the smuggle request. So when this is sent to the ICM, it will place the smuggle request in the backend, and it will wait for more data. So when a victim sends a request, he will receive a redirect, as we already saw, that will send him to the malicious domain, which is controlled by the attacker, and it will send also the session cookies and everything at the first, in this case, 200 bytes of the request. If we follow the redirection, what we are going to see is that the evil server actually received this data, so we already have the cookies of the victim, but also it responded with a form that will continue the attack. So now the victim will become the attacker, and this will create a botnet that will persist the attack as long as we want. But after seeing this vulnerability, I wanted to know more about the ICM, so I started looking at the different features that it offers. And what's interesting is that the ICM, when it's configured for Java, for a Java process, will accept pipeline requests. This is something expected from the RFC, but in ABAP, this is not by default. So this means that the ICM will allow to receive a concatenated request in the same payload, and when this happens, the worker thread will actually store both requests in the same MPI buffer, but when the HTTP parser recognizes that there is an extra request, it will reserve a new MPI buffer, and it will place the request there. So now the worker process will continue processing the worker thread will continue processing the first request. It will send it to the Java process. The Java process will generate the response. It will place it in the MPI buffer, send it to the worker thread, and the worker thread will forward this response back to the victim, or to the client, actually. Now the MPI buffers will be freed one by one, the references will be lost, and the request response cycle will be completed. And now the worker thread will start processing the next request that was stored in another MPI buffer, because this was a pipeline request. But what about sending a long request with a pipeline request at the end? So let's say we send a request which is longer than 65 kilobytes, and at the end we send another pipeline request. Now the worker thread will reserve a buffer again. It will place the first 65 kilobytes there. When it's ready to send it to the Java process, we'll store the other part in another MPI buffer, and the HTTP parser will recognize that there is an extra request. So again, it will reserve a new MPI buffer, and it will place the pipeline request there. Now, of course, the worker thread will send it to the Java process, the first two buffers. It will generate a response, place it in the shared memory, send it to the worker thread again, and the response will be forwarded to the client. But remember one thing, when we send a long request, the buffers are not free one by one. Instead, they are going to be, the MPI free of buffers is going to be used. And so all the buffers associated with this worker thread will be freed. And that includes the MPI buffer that was used for the pipeline request. So now we have a reference to a free MPI buffer, and when we try to, of course, the reference is not lost when the MPI buffers are freed. And so when the worker thread sends this to the Java process, we will see an error raised because the worker thread thinks that there is no buffer being used. So what can we do with this? Well, of course, we can have a reference to a free MPI buffer, and if another TCP connection, another worker thread, tries to store a request in the shared memory, if we are lucky enough, it will reserve the same MPI buffer that we were using. And actually, this is going to happen a lot, because the MPI handler actually allocates the free buffers in a list that is actually a stack. Even though SAP states that this is a queue, after reverse engineering the ICM, I noticed that this is not a queue, this is a stack. So free buffers are going to be used a lot, again, once over and over again. So the worker thread 2 will place the request there, and it will modify the buffer, and of course we will have a different value inside the MPI buffer. But if we try to get the response from this, we will still have an error because the worker thread 1 believes that there are no buffers used. So what we want is to write in the same position after a victim places his request. And we are going to do it by sending an incomplete pipeline request. So when we send incomplete requests, the worker thread waits for more data. And incomplete requests are going to be any request that does not contain 2 line breaks after the headers, or that contains a body shorter than the message length header was stated. So when the worker thread tries to read this request, it will parse it, and it will be set again to read mode because more data is required. So when this data arrives, then it will be written at the end of the MPI buffer, and it will be written at the position that is stored in the offset. So each worker thread has an offset for each MPI buffer. As you can see, if we send first some data and then we send more data, it will be placed in the same memory address. And the offset of this buffer will be modified. So again, let's see an example. We will send a request, a long request, with an extra byte, which is the pipeline request. It will be stored, the first part, it will be stored in the MPI buffers, and then the HTTP parser will recognize this, and it will place the extra byte in another MPI buffer because it will believe that this is a pipeline request. Again, the first part will be resolved, a response will be generated, it will be placed in the shared memory, forwarded to the worker thread, and the worker thread will forward it to the client. Now all the buffers will be freed, and we will have the reference to this place, but when the worker thread tries to parse this pipeline request, it will stop, and it will be set into read mode. Now, if we are lucky enough, a worker thread 2 or a client, a victim, will send his request, and the worker thread will reserve the same MPI buffer. And when this happens, you can see the MPI buffer at the top. The worker thread 2 will have the offset 55 because it has written 55 bytes. The request will be placed there. And if the attacker then sends a request or the rest of the request, he will be able to tamper the request that the victim issued. So now when the worker thread 2 sends the MPI pointer to the Java process, the Java process will actually use the new request that was modified by the attacker. So this will generate, for example, a malicious response, will be placed in the MPI buffer, and the worker thread will forward this back to the client. Okay? So again, the steps to reproduce this attack is the attacker needs to hijack an MPI buffer, the victim will send a request that will be placed in the same MPI buffer, the attacker will then tamper this data, and the victim will receive the malicious response, which in this case, for example, if we send a get to start page as a victim, in some cases we will receive the redirect to evil.com. And we can use the exact same attacks in the previous example, in the previous vulnerability, and any attack of HTTP smuggling exploitation will be successful. And also, we will not need a proxy because we are actually tampering different TCP connections. So we can make this attack even without a proxy, but it is less reliable. But if you see at the image, you will notice that some of the responses do not contain a status code, and that is because in some cases, we are not tampering the request buffer, but instead we are tampering a response buffer, because MPI buffers are multipurpose. So we can use the same MPI buffer for a request and a response. So again, let's say we already have an MPI buffer hijacked, and a request arrives from the victim. And in this case, let's say that the victim does not reserve the same MPI buffer but another one. This is just a timing scenario, depending on the time when we send one request and the other. In some cases, one buffer will be used, and in some cases, another. So in this case, another MPI buffer will be used for the request. It will be sent to the Java process, and the Java process will generate a response that will be placed, in this case, in the MPI buffer we have hijacked. So now the response will be placed there. And if at any of this, if at this point we are able to send more data, we are going to be able to tamper not the request but the response. So we will be able to place anything we want. We will be able to write an arbitrary response that will be sent to the client. So when the worker thread 2 sends, before sending the request, it's going to parse the response. The response is going to be parsed. It will send it to the client, and if you notice, the MPI buffer, you will see that there is an extra header that I included there. And that is SAP cache control header, which is an internal header used to select which responses should be stored in the cache. So what's going to happen is that the cache handler will think that this response should be stored in the cache. Therefore, it's going to see what was the request URL, and it will store the response for that resource. And we can even play the role of the victim. If we, instead of sending just the attack, we can also send a lot of requests to actually modify any URL we want. So we will be able to poison any URL and to create a response completely arbitrary. So we can place a script, we can place anything we want by using the SAP cache control. So we are going to see a demo of this attack. And remember one thing. If we are able to, this is not reliable, this is not really reliable. We will need some attempts, not a lot of attempts, but it's not going to happen in one attack. But if we are successful for only one attack, then this response will be stored. So it will be persisted forever if we set a big SAP cache control max age value. So as you can see, we send a request to start page and nothing strange happens. Okay, we just get a normal response. But we are going to try to poison this start page URL. So I'm going to use a small script I wrote in Python that is going to first try to hijack different MPI buffers. Then it will send a lot of requests to start page so that we are able to modify those responses. And then it will try to tamper the data of these responses. So it will try to place the SAP cache control in this response and also a malicious script. Of course, we are not going to be able to hijack this buffer and modify the response in just one attempt. We are going to need to send a lot of attacks. Actually, not a lot, a few of them. So, as I said, after one of these attacks is successful, the start page will be modified and the script will recognize this. It will change the times to try to be able to do it. And again, as you can see, after a few attempts, we were able to modify the start page. So now, when a victim or any client requests for the start page, he will actually receive a different response, which contains a script and an arbitrary HTML. Okay, so with this, we are able to modify anything we want from the application. But still, there is something else we can do. And that is to try to modify or to try to tamper the memory of the cache of another file. And I'm going to show you how. So I said that we were going to try to modify the response just before the response parser is called. But what if we try to do it after that? And that is just a matter of luck, of course. But after sending a lot of requests and attacks, we might be able to do it. So if the response is not modified, and actually the response for the request that the victim issued had a SAP cache control, the response, of course, will be parsed, will be sent to the client, but then the cache handler will be called. At this point, we hadn't modified or we hadn't tampered the response. So the cache handler will actually create a file, because cached objects will be stored in a file. And in this file, it will place some special headers. These headers will tell information about the response, such as the length of the entire response, the length of the body, and some other information that is not quite important. And if we are able to modify or to tamper the response at this specific point, then the cache handler will place the response in this file, and it will not match the headers that it created. So when another client sends a request to the ICM and to this specific resource, which is corrupted, the request cache handler will be called, it will find a reference in the cache, and it will use this file to generate a response. And this response will not be placed in the shared memory, as we already saw, but it will be placed in a heap buffer. And the length of this buffer will be set using the headers. So in this case, it will be 85 bytes. But the actual response was longer than 85. So we are going to be able to write in this buffer and actually obtain a heap buffer overflow. Okay? And we have proven that it is possible to modify other data structures that were in the heap so that we can overwrite different address pointers and eventually obtain remote command execution if we are able to defeat memory randomization. So SAP created 2 CVEs for these vulnerabilities. Actually, I reported some other vulnerabilities, but these were the most interesting ones. And the first one was a CVS-10. As I already proved, it's possible to hijack all clients. And the second one was an 8.1 because they stated that the attack complexity was high and the scope was unchanged. We do not agree with that, but that is what SAP stated. And also, this is quite critical because it affects all the SAPs in the world. We can choose any SAP and it will be vulnerable to both of these attacks. And this includes Java, ABAP, S/4HANA, which is in the cloud, Web Dispatcher, which is the load balancer used for most SAPs, and well, any SAP product. They also released 2 security nodes and a manual workaround that can be implemented in both the NetWeaver and the Web Dispatcher. And finally, we at Synapsys created a detection tool that will allow clients to know if they are vulnerable to this or not. So finally, some conclusions. It was interesting to see that HTTP servers are great targets for attackers because not only they are exposed, as we already know, but reverse engineering one of these components is quite easier than one might think because remember, the HTTP server must be compliant with the RFC, so we know what the HTTP server is going to do. We can predict what is its functionality. And most HTTP servers have same functionalities and workflow, even though the internals might be different. And also, it's really important to be able to recognize where the requests and responses are stored in the memory so that we know what are we going to be able to modify and not. Also, it was really interesting to see that it is possible to escalate low-level vulnerabilities that in the past were not exploitable, okay? Because, for example, in the past we are not going to be able to exploit, or we are not able to exploit use after freeze in an HTTP server. But using these advanced HTTP techniques, we are going to be able to, of course, modify invalid header. We are going to be able to modify the application by using attacks that do not rely on HTTP headers, or we are going to be able to bypass VPNs by using DNS rebinding and create botnets. And finally, we can see that ICM, which was the code name for these vulnerabilities, was really important. They were considered to be really critical. They were addressed by the Cybersecurity Infrastructure Security Agency of the US. SAP stated that these were probably the worst vulnerabilities in years, and because it affected all SAP installations, and they were accessible through a really exposed service that was actually exposed in the internet in a lot of different companies.